Okay, so in this video, we are primarily concerned with particularly this, which is, so first of all, this is our neural net, right? Like a 3-unit neural net taking 2 inputs. And we're particularly concerned with the empirical, like the blue line. So this is if you randomly instantiate, like, I think 2,000 of these, and then you figure out which Boolean function it computes. And so the probability that it's computing one of the parity functions, aka XOR, that's like an entire sentence that's composed of 6 letters, is very small. So the probability of the parity functions is very small. And so we're just like, why? And also, obviously, like the constant functions are very large. And we kind of, I think, we kind of might, that might be another video. But for now, we're just looking at the parity functions and like, why are they so infrequently represented by a randomly sampled neural net of this particular architecture? So, okay, so the observation, or like one observation, is that to compute one of the parity functions, right? So if we look at the, if we just look at a hypercube, it's like this is a hypercube. The parity functions have to group opposite corners together, right? So, but the output unit, like this unit, all it can do is represent a decision boundary, like a linear decision boundary. And so what has to happen is that the first layer has to remap. It has to remap opposite corners. So, like, in other words, it has to assign them new coordinates so that the opposite corners are linearly separable. And so I think that's so basically what that is saying is that if you consider the line, like the 2 line segments connecting 2 opposite corners, what has to happen is that the first layer has to unintersect the 2 lines. I believe that's a necessary and sufficient condition for the linear separability of the 2 sets of points. I'm like 98% sure. So, yeah. So the first step for this neural net to be able to represent a parity function is what's happening down here. We have to unintersect the line segments where the 2 line segments are. You connect opposite corners. So I don't have the other one illustrated here, but there's like 2 line segments and you have to unintersect them. So that's kind of what we're looking at in this video, is just how frequently does that actually happen. If we, so what we're doing is we create a neural net that so it's just the bottom layer. So our neural net is just this, 2 inputs, 2 outputs. And then we're computing, so then we're passing the corners of the hypercube, like -1 and 1. We're passing the corners of the hypercube into the neural net that we just randomly sampled. And then we use this formula that I got off of Wikipedia, which is how you apparently calculate if 2 line segments intersect or not. I'm not going to explain that because I don't frankly understand it entirely. I mean, I think it's basically like you solve a system of linear equations and then you check that the solution is contained within each line segment. And so the way you solve the system of equations is like the determinants, and like this has something to do with the determinants. So anywho, yeah, we're just checking for intersection, and like in particular, these are where the two line segments were unintersected, right? Because they always start off at like -1, 1, 1, 1, -1, -1, 1. And yeah, so like these were the successful cases where, right? So you can see like the output unit can separate the two corners because it just puts a line here, puts a line here. Some of these look like, I mean, I guess maybe that's technically separated if there's just a very small space. Yeah, I mean, this one doesn't look correct, but so, yeah. Most of them look correct, though, so I don't really know what to say. Yeah, like here, there's like a very small space. So I'll assume like on these, there's a small space, but I don't know. And, okay, so anyway, the overall result is that 70% of the time, the two line segments intersect. And so 30% of the time, they no longer intersect. And so yeah, so that's an empirical result. And I mean, maybe it's I mean, I still don't know where that, like, why it's 70-30. So maybe I'll look into that later. But I mean, it kind of gives a little, I guess, insight into these statistics where like these are so small. Because to like compute these, you know, only 30% of the time is it even possible to compute these, because you have to unintersect the lines. But then, even if you unintersect the lines, the output unit has to fit its decision boundary, like in between the two unintersected line segments. So that's, I guess, like, you know, that gives like high level, I guess, intuition as to why these functions are so hard, or like so rare in the weight space. But yeah, I mean, I still don't entirely understand like this 70-30 distribution. Like, I mean, certainly the line segments start out intersected. So I mean, I guess it, like, there's some argument there that it would make sense that they typically would remain intersected. But yeah, but I don't know. So so that's a video for you.